Okay, it's time for another physics problem. Again, you can see these things appear. That means it's a test that I wrote. This is an old test, and I'm going to take the test for you. It's going to be fun, right? And I have to say, I wrote this a while ago. I don't even remember what it is, so it's not like I practiced solution. I'm just going to work through it just like you would. Okay, so a frictionless train car has a mass of 2,000 kilograms in the moving in the positive x direction with the 5 meters per second. So now's the time to draw, right? So let's just go ahead and draw like this. There's my train car. It's moving this way. I can put let's call it MA equals 2,000 kilograms. So here's a trick that I learned for collision problems. You don't want to call the objects 1 and 2 because you're going to do, let's say you want V1 before the collision. What are you going to call it? V11? That works, but it looks confusing. If you use A and B, you can do VA1, VA2, and it works. So this is VA1. VA1 equals 5 meters per second. It collides with another frictionless train car with a mass of 3,000 kilograms. This is MB that was at rest. So VB1 equals 0 meters per second. And then after the collision, the first train car bounces back in the negative x direction. So here's A with the speed of VA2 equals negative 0.5 meters per second. And the originally stationary car moves in the positive x direction. After the collision, the train car bounces back in the negative direction, and then another one moves. Was this an elastic collision? I mean, I'm thinking right now that you can't tell. But let's just proceed. Let me make sure I got everything. And yes, remember, who wrote this question? This guy right here wrote it. So if it's a bad question, it's my fault. So 2,000 kilograms, 3,000 kilograms, got that. This is 3MB, 3,000 kilograms. Collides with another frictionless train car at rest. After the collision, the first train car bounces back. Okay, I think you can do it. Okay, so remember, this is a collision. And the one thing I know for sure in a collision is that if the forces between... This is after. That's my time thing. After. And so this is VB2, which I don't know. Okay, so one thing that we do know is if the collision is very, very short and there's an interaction between the two forces, then the momentum must be conserved. So this says P, and we're in one dimension here. So P total initial equals P total final. That's what that says. P is momentum. So I can write this out as an expression. There's going to be MA VA1 plus MB VB1 equals MA VA2, that's negative because I'm using scalars, plus MB VB2. Okay, now I know at least one of these things is 0, and that's this. I know everything else. I can actually solve for VB2 because it wasn't given. If momentum is conserved, I know what that is. So let me solve for VB2. So I'm going to subtract this from both sides, and I get MB VB2 equals MA VA1 minus MA VA2. And then I can divide both sides by MB, and I get VB2 equals MA VA1 minus VA2 over MB. So if I put in my values for that, I get MA is 2,000. VA1 minus VA2, I can put in VA1 is 5. I'm going to leave off the units. Minus a negative 0.5. So minus negative, so it's going to be plus 0.5. And all of that divided by 3,000. So let's get that value with my handy dandy calculator here. I put a new piece of tape on there so it works a little bit better. Okay, so I get 2,000, enter. 5.5 times 3,000 divided by. And this is 3.67 meters per second. Okay, now the question. Is this an elastic or inelastic collision? Okay, that's a different question. But this has to be true because momentum is conserved. So if this is an elastic collision, the total kinetic energy before is equal to the total kinetic energy afterwards. So I know all the masses and velocity, so I can calculate that. So let's do that. So let's say if elastic, K total 1 equals K total 2. So this is going to be 1/2 MA VA1 squared plus, I'm not going to write out the second one because it's 0, equals 1/2 MB VB2 squared. I don't know why I didn't put the A first, plus 1/2 MA VA2 squared. So I know all these values. So let's just calculate this right here. K total 1 is going to be 1/2 times MA, which is 2,000, times VA1, which was 5 squared. Handy dandy calculator time. Okay, drop. So 0.5, enter, 2,000 times, which is 1,000. I didn't need to actually do that, but I did it anyway. 5 squared is 25, but I'll do 5, enter squared, times, and I get 25000 joules. Now let's do K total afterwards. It's going to be 1/2 times mass B, which is 3,000, times velocity B, 3.67 squared. Now here you do have to worry about once you start rounding numbers and squaring them, you can cause problems, but if it's close, I'll be okay with that. And then plus 1/2 2,000 times VA2, which is 5.5 squared. You'll notice that kinetic energy has to be positive. Okay, that's just a side note there. So let's put this in so I get drop. So 0.5, enter, 3,000 times 3.67, enter, squared, times. So there's my first kinetic energy. Now I'm going to go to the next one, 0.5, enter, 2,000 times 5.5 squared times plus. And I get 50453 joules. So what does that tell you? Okay, that tells me that final kinetic energy is greater than the initial kinetic energy. Is that possible? Absolutely. Okay, it could be maybe the two cars are colliding and there's a compressed spring over here. And so when it hits, that spring, it releases its energy and adds extra energy to the situation. It doesn't change the momentum because it's an internal force, but it does change the total energy of the situation. Okay, so in this case, it's not an elastic collision. It's a hyperelastic collision. It has more kinetic energy afterwards than before. Is hyperelastic kinetic energy a word? I don't know. Maybe I just made it up. Okay, but there you go. Collisions in one dimension.